Well, thank you. Let me express my appreciation to Chris and Nigel for inviting me and for organizing this very stimulating 3-day conference. What I'm going to be talking about, perspectives on the half-full Landau level, I'm afraid probably doesn't have too much obvious connection with few-body systems, and actually I'm not exactly sure I'd say it's has that much connection with the fractional quantized Hall effect. It's more what I would call the unquantized quantum Hall effect, because we're trying to ask what happens at for a half-filled Landau level when you do not have a fractional quantized Hall state where there is no energy gap. This is an old problem that I've been interested in, of course, for many, many years, more than 20 years. But there is new excitement in the field, and so I thought that it might be something that people would want to hear about, even if it's slightly off the main topic of this conference. And I guess Sentil feels the same way, because I think he's going to be talking about the same problem from a slightly different point of view. The work I'm going to talk about was done, it's all work in progress. It's not written up, and some of it's just evolved in the last week or so. It's been done in collaboration with Nigel, with Chang Wang and Adi Stern, but I haven't consulted with them about the talk, so I don't guarantee that they agree with things that I'm saying. So if I make a mistake, it hasn't been approved by them. Including Nigel. I told him roughly, but not everything let's see. So, whoops, somehow this is a little compressed here. But anyway, the motivation behind this, somehow, I don't think this is, somehow it hasn't come out properly. It's only, no, I'm not sure what's going on here, but I'm not getting the whole slide in. No, I'm missing the top half of the slide. Whoops, there it goes. Now it's coming. I don't know why I wasn't there before. Okay, so as I said, there have been recently some very exciting developments that have focused new attention on this old problem. In particular, there was some very beautiful work by Damson about a year and a half ago now, I think, or 2 years, and subsequent articles by many authors, some of whom are in this room, which pointed out that you could describe the half-fill Landau level in terms of Dirac fermions instead of the non-relativistic composite fermions that basically we used, and I think in some sense that that Jananja is using and that we used in this original paper that I wrote with Patrick Lee and Nick Reed, which I will refer to as HLR, which people seem to use, and much related, a vast body of related work that has followed in subsequent decade or so, and which differed in some important ways from the Dirac fermion, or appear to differ. And this new theory has generated some, I think, very important insights, and it's helped understand certain things are much clearer with the Dirac theory. But I think some of the papers that have been written also have generated some confusion among, maybe there's no confusion among the experts, but there seems to be at least confusion among bystanders. And particularly they want to know, are these theories equivalent or are they fundamentally different theories? If they're equivalent, what's the relation between them? What I would like to try to convince you of is that, at least my conclusion, or our conclusion, is that, well, of course, the Dirac description, as I said, has some very important advantages. It's simpler in important ways. Particularly, it's simpler if you consider what happens in the limit where, say, the bare mass, you have electrons in a magnetic field, you take the bare mass to 0, keeping the interaction strength fixed. So that projects everything down to the lowest Landau level, or a single Landau level. And once you confine them to a single Landau level, there's an exact particle-hole symmetry, about half filling in that Landau level. And if you're at half filling, then there is already a particle-hole symmetry. And that symmetry is manifest in this new Dirac theory, but it's not manifest in the, at least in the usual formulation of the HLR theory. And so that's what caused people to think that maybe they're two really different theories. And some people have even suggested that there's a phase transition from one to the other, or from more than half filling to less than half filling, because in the HLR theory. And I will argue that that's not the case, that the theories are really fundamentally equivalent, and the HLR approach is in fact perfectly capable of describing this particle-hole symmetric limit, but you have to be a little more careful. It's not as obvious because it's not manifest. It's a hidden symmetry. And what I will talk about, I'll try to explain how I conclude this, or how we conclude this. And again, as I say, it's work in progress. There's some details still to be worked out. And I was going to say something, I may say something about trying to elaborate on the relation between the two theories, but since Senthil will probably present the Dirac theory in much greater detail, I probably won't say much about the Dirac theory at all, but concentrate on the HLR results. So the bottom line, as I said, is that particle symmetry is explicit in Dirac formulation, but not in the HLR formulation. And as I say, the thing that people have most focused attention on is that if you use the HLR formulation, at least in a relative naive sense, it doesn't have complete particle-hole symmetry. It actually does have particle-hole symmetry in a sort of obvious way to lowest order in deviations from filling fraction of half. But if you go to the next order in delta nu, up to delta nu squared if you want, you don't get a particle-hole symmetry. And also there's some issues of what happens when impurities are present. So I'm going to try to argue that in fact you do get this quite consistently in HLR, even up to second order, even at the RPA level. I should say that to get the correct response at finite frequencies, which is in some sense a particle-hole symmetry issue, you have to include in HLR the effects. You can't just use it as a Hartree, as an RPA theory. You have to include in it Landau interaction parameters, as you would in any Fermi liquid theory, and particularly you need the F1 interaction parameter if you want to restore Galilean invariance and if you want to get the right frequency dependence. And I would say, but that's also true in the Dirac formulation. You will not get finite frequency results correct unless you include things like the F1. So that part is the same. Okay, so to remind you, the physical problem that I want to solve, that I'm talking about, is I'm talking about spinless electrons, or completely spin polarized electrons, in a semiconductor in a magnetic field. And for simplicity, I'll assume a quadratic band structure, so that we have a Hamiltonian. H naught is our starting Hamiltonian, so it's a p minus a squared term over with some effective mass m, which is I call it the bare mass or the band mass. It's not it would be, let's say in gallium arsenide, it would be 1/15 of the free electron mass, but I'm assuming a quadratic spectrum. And then there's a two-body interaction, which depends on only the separation between particles. I can add impurities, which will be a one-body interaction, but for the moment there are no impurities. And I'm using the vector potential here is just the vector potential due to a uniform magnetic field B, which we can use in whatever gauge we want. And I'm going to use units where E and H bar are equal to 1. Okay, and particle-hole symmetry, as I said, is if you take the limit of the bare mass going to 0, which pushes the cyclotron energy all the way up to infinity, but keep the electron-electron interaction fixed. Then we project onto the lowest Landau level, and there's an exact symmetry, a mapping for every quantum state at filling fraction nu. There's another one at 1 minus nu. All the energy gaps are the same, and there's just some simple relation between the total energies in those systems. And one of the consequences, and this is true not only once you project on the lowest Landau level, not only is there symmetry as far as the energy states are concerned, but also for dynamic properties, including transport properties. And one of the properties that people have focused on is that if you're sitting at half filling, and you have particle-hole symmetry. You're in the lowest Landau level, and if I look at, say, the response to an uniform AC electric field, my conductivity sigma xy of omega is going to be precisely 1/2 E squared over H for all frequencies. It's just half of what you get for a completely filled Landau level, independent of the frequency of the applied field in this limit of the cyclotron energy going to infinity. And in our units, where E squared over H bar is 1/2 pi, this becomes 1/4 pi. And this should also hold if impurities are present, provided, a very important provision is that the impurity potential has to be particle-hole symmetric, at least statistically. We can have positive impurities and negative impurities, but we want to have equal numbers of positive impurities and negative impurities of the same strength, or more generally, I have some impurity potential which fluctuates from position to position. I can always choose it so that the average is 0, but I also want all odd moments to be 0. Okay, so it's completely symmetric between V and minus V. That's what I mean by a particle-hole symmetric impurity potential. Okay, so how do we approach this problem? So in the HLR approach, we began with an exact transformation. There are different ways of doing this. There's a singular gauge transformation. It includes you basically multiply the wave function by a phase factor, which introduces a Chern-Simons gauge field into the Hamiltonian. There are precisely 2 flux quanta of this fake Chern-Simons field attached to each fermion, and you wind up with a transformed Hamiltonian, which is better to write in Lagrangian form, which has the form. It is just a precise translation of the problem. It has the Lagrangian for fermions in some vector potential. This is D is the operator derivative with respect to position plus I, and now there are 2 vector potentials here. There's the external vector potential A, and this new fake vector potential, Chern-Simons potential little a, and here the fermions see them both, and these fermions, I will often refer to them as composite fermions. They're very similar to what Jane talked about, but a little bit different in some details. And then, in addition, these interact. There's an interaction term, which I won't bother to write out, which is the 2-body interaction. And they interact with this gauge field. This little gauge field has a Chern-Simons interaction in it, which I use the notation ADA, which is basically epsilon mu nu lambda, A mu D nu A lambda, where these are the X, Y, and coordinates and the time coordinate. And one of the consequences of this, when you take the variation with respect to A0, is that it imposes a constraint that the curl of this fake vector field is minus 4 pi times the density of the composite fermions, which is actually just the same as the density of the electrons. So it's minus 4 pi NEL of R. Of course, this is something which can vary from point to point. In fact, it's the sum of delta functions. But of course, what we're going to do is average this and talk about an average magnetic field. And again, I should emphasize that this HLR work was based on many antecedents, of course, very importantly on the fractional quantum Hall theory states by Jane, and also work by Lopez and Fratkin, which incorporated Chern-Simons fields into this fractional quantum Hall description. And there was also some simultaneous work with some overlap about filling fraction and a half by Meyer and Zhang, although they didn't really talk about dynamics, which I'm going to be talking about. Okay, and so now so this was an exact transformation. So we've just transformed one insoluble problem to another insoluble problem. But the point is that we can now make a hypothesis that we can now make do mean field theory on this new problem and get a reasonable starting point for description. Whereas if you try to do mean field theory on the original problem, you get nowhere because you have a ground state in the absence of the electric field potential, which is infinitely degenerate. So here we have now a ground state which at least is not going to be degenerate, and we can talk about, we can hypothesize that the true properties of this system, ground state and excited states, can be obtained from this ground state by using perturbation theory to take into account the effects of fluctuations in the gauge theory, which we will, of course, be ignoring in the ground state. I mean, field ground state, we ignore fluctuations we just assume an average magnetic field, which is contributed by the average electron density, but because the electron density fluctuates quantum mechanically, there are fluctuations in the gauge field, and also the Coulomb interactions, which in mean field theory just become just a constant. Now we have to take into account those fluctuations. And but we're assuming that when you do that, you can do this in something by summing up an appropriate set of diagrams in perturbation theory, or one way or another, adiabatically turn on the interaction strength and go from the ground state, go to the ground state without having a phase transition. That's the assumption. And it's not a completely trivial assumption. It's not necessarily right. It has many implications. It says that there should still be a Fermi surface of some kind when we turn on the interactions, and there are various predictions that follow from it for physical observables. But as I say, it's not necessarily true. It depends on the form of the electron-electron interaction at short distances, whether this is really true. And in fact, we know that in many cases it's not true. For example, in the third Landau level, it's not true. The ground state is not a Fermi liquid. It's some kind of charge density wave state, or a striped state, or a pneumatic state, or something. But it's not a Fermi liquid. Of course, in the second Landau level, we get the Pfaffian state. We get some kind of quantized Hall state with an energy gap. So it can break down, but it looks like, at least in the lowest Landau level, as far as we can see, this is the correct ground state to some, at least to very, very low temperatures. Okay, so now there are a lot of complications in all of this. One is that if you have 1 over R type Coulomb interactions, the ground state is not actually a Fermi liquid. We can actually show that there's a logarithmic divergence in the effective mass as you approach the Fermi surface, so it's not really a Fermi liquid, but we think it's some kind of marginal Fermi liquid, and many of the properties are almost exactly the same as a Fermi liquid, and you can take into account these logarithmic divergences without too much difficulty, and we think we know what's going on. This is due to infrared divergences in the gauge fluctuations. If you had short-range interactions, then the density fluctuations are much bigger at long wavelengths, and then the gauge fluctuations are much worse, and then it's not even a good Landau Fermi liquid at all. The lifetime becomes comparable to the energy. But again, we believe that there is still a Fermi surface, and there's some predictions that still hold. I don't want to get into this, because in talking about the difference between the Dirac theory and the HLR theory, this is irrelevant, because they have exactly the same divergences in both theories, and we want to not worry about those. So the point is that if we assume an interaction that falls off slower than 1 over R, then you can suppress these divergences, and that's what I'm going to do. So you can assume that we have an interaction that goes as 1 over R to the 1/2 or something like that at long distances, and so we really do have a well-defined effective mass and so forth. Okay, so what are some of the predictions? One prediction, of course, is the ground state at filling fraction 1/2 should be compressible. There should be energy gaps if I go to the Jane fractions of nu is equal to, I write them differently. I write it as p over 2p plus 1. P can be the positive or negative, and that corresponds to when John Anger writes it, he writes p positive but puts a plus or minus 1 here. These are the same. And they refer p greater than 1 is nu less than 1/2, and negative p is nu less than 1/2. And so we predict, just as he does, of course, that there will be energy gaps there, for just the reasons that he said. The problem reduces to these composite fermions in an effective magnetic field, which is proportional to the deviation from filling fraction 1/2. In addition, the analysis makes a prediction which is correct in the absence of these divergences for the relative sizes of the energy gaps as you get closer to nu equals 1/2. Basically, you're getting an energy gap which is like the energy in this effective magnetic field. So the energy gap would then decrease linearly or would be proportional to delta B, or the distance from nu equals 1/2, as you get closer and closer to nu equals 1/2. It predicts, of course, in the absence of impurities, you get a DC Hall. You get a DC conductance, which is just the Hall conductance, and there's no longitudinal conductance. Less trivial, and one of the things that excited us most was let's calculate the conductivity at finite wave vector in the limit of omega going to 0. This with the longitudinal conductivity. So Q is in the x direction, and I'm calculating sigma xx of Q. And we made a prediction that this should have the form of the wave vector Q divided by 8 pi times the Fermi wave vector Kf for a system without any impurities, and that there's no adjustable parameters in this theory, and in the presence of impurities, this would hold only for wave vectors Q that are larger than, that should be the inverse of the mean free path. At short wavelengths, this gets cut off. So what you can see here is that Q goes to 0, sigma xx would go to 0 in the absence of scattering, which is what you would expect. That's what I said. At the DC conductivity in the absence of impurities is just, there's no sigma xx, there's only a sigma xy. But with impurities, then you get a finite resistance or a finite diagonal conduction here that should be proportional to the to 1 over the mean free path. This is actually studied by looking at the surface acoustic wave velocity at Q at nu equals a half, and Willett saw that there was this wave vector dependence, which we could explain. The numbers don't agree exactly, but they're within a factor of 2 or something, and I think they're uncertainties, so we don't really, but at least qualitatively this is correct. And what was also realized that if you go away from Q equals a half, again, this dependence applies at large Q, but at small q it's cut off by cyclotron orbits, and it leads to oscillations in the surface acoustic wave properties, and also in transport properties in the presence of post-periodic potential. And I will return to this. This is also an important thing to look at, what happens as you move slightly away from nu equals a half. But before I return to that, so let me emphasize that within this approach, if you say, let's just, we have a theory that we can't handle exactly, so the simplest thing is to make an RPA approximation. And if you do that, all of the properties that I talked about, you can predict correctly from RPA, but there's some drastic errors in it. The most important error is that it has completely the wrong energy scale. If you try to look at energy-dependent phenomena, not just low-frequency phenomena, in particular, it ignores the renormalization of the Fermi on effective mass. And as Janandra pointed out, I think if you take the bare mass going to 0, so the cyclotron energy goes to 0, the effective mass and the energy scale for all the fluctuations remains finite, and it's set by the electron-electron interaction. So we would say that there's a renormalized mass m star, say in Fermi liquid theory, an m star, which remains finite when m goes to 0, and it's controlled by the electron-electron interaction. And if you want to calculate, say, the specific heat, you need this effective mass. Or if you want to calculate the energy gaps when you go, not just the relative size of the energy gaps, but the values of the energy gaps, when you go away from nu equals a half, you need this effective mass. So we must, if we want to get agreement for these things, we must at least replace the bare mass by the effective mass, and the effective mass, when the bare mass goes to 0, what happens is that you get rid of all the effects of the higher Landau levels, and there's a renormalization process, as in any renormalization group. So if I want to look at the low energy theory, I have to renormalize the mass. Okay, so you can do a naive renormalization in which you simply replace m by m star. I'll call that HLR RPA star. And of course, we can't calculate the effective mass within this formalism. That's a high energy theory. You have to do it some other way. But you can measure it, or we can maybe calculate some other way, and we put it in. And then of course, we've done it so that we get the energy scale right. But it's still not right, because when you renormalize the mass, you should always also look at interactions. You're going to generate Fermi liquid interactions. We know that from Fermi liquid theory. So they're Fermi liquid parameters which become important. And if you don't keep track of them, you won't get many properties right. For example, the most important one is the finite frequency response to a uniform electric field. And in particular, if you use omega, if you calculate the response for omega different from 0, it violates Cohn's theorem, which basically says if you have a system with one type of carrier, quadratic dispersion, so it has basically Galilean invariance, then the response to the time reversing a uniform field should be unaffected by electron-electron interactions because the electrons just move and carry the interactions with them. And so in particular, if you look at the response to a circularly polarized field, it's given just by the density of electrons times I times the mass divided by omega plus or minus omega c, where omega c is the cyclotron frequency, B over m, and in particular this gives you a pole, which you must have, at the bare cyclotron frequency. And if I simply put in m star, then obviously my pole would come at the wrong place. I would see that it would occur at B over m star rather than B over m. And also if I want to say, well, let me just look at low frequencies, not the cyclotron frequency, but expand about 0 frequency, I'd also get the wrong answer because if the lowest omega equals 0, of course I get the right answer because the mass drops out. I would get the Hall conductance. But then there's a diagonal conductance which is predicted to go as I omega times m star over b squared. And if m star is, but it should be really m. In other words, if the correct expansion should have an m here, and instead I have an m star. But once I put the Landau Fermi liquid parameter in, if I do that correctly, it restores this to an m star. And in particular, if I now say, let me let the bare mass go to 0, then this term drops out, and I find that with the F1 parameter in, I get a response function which is completely independent of frequency. So of course it has the correct value that sigma xy is 1 over 4 pi at nu equals a half at all frequencies. So that's a restoration of particle hole symmetry, if you wish, by including this F1 parameter. Okay, and just to remind you what the Landau interaction parameters are, if we have a distortion of the Fermi surface and we expand it in circular harmonics, then there's an effective Hamiltonian which goes as the V star, Vf star kf over 4 pi. It would be a sum on the squares of these distortions if there was no Fermi liquid parameter, and then but we have to add this FL for the L is the angular momentum component, and F1 is what you get from Galilean invariance is that F1 must be equal to m over m star minus 1, or the Fermi velocity star over the Fermi velocity minus 1, and that's what you need. You also need, for example, the F0 parameter if you want to get the compressibility, because the compressibility of the system is not given by the effective mass, but d mu dn is actually proportional to 1 plus this F0. So again, that's something you would need it for. Okay, so we've seen how to restore particle hole symmetry in the presence at finite frequency in the absence of impurities. But what has attracted more argument, and really I think was in some sense perhaps the motivation for Sohn to really get involved in this problem, is an old paradox that was pointed out by Kivelson in 1997. Kivelson and co-workers in 1997, that if you want to have sigma xy equal to 1 over 4 pi, which is what we require by particle hole symmetry in this particle hole symmetric state, then if you this actually requires, if you want to have particle hole symmetry, then that means that sigma, if I look at just the composite fermion part of the ignoring the coupling to the gauge field, that should be equal to 1 over 4 pi. But naively at least, if you say, well, the composite fermions see an effect, they're particles moving in an effective magnetic field, and then I'm putting in impurities which half of them have positive magnetic field and the other half have negative magnetic field. So statistically there's no magnetic field. So you would say, well, these are particles moving in a system that has time reversal symmetry. They should have no composite fermion Hall conductance. So therefore sigma f, CFXY should be equal to 0, at least naively in this theory, and that does not lead to the correct value of, what it leads to is that there's small corrections to sigma xy. The actual sigma xy is not equal to 1 over 4 pi, but it has some corrections which are proportional to rho xx squared, which is to say it's proportional to the square of the density of impurities if you start adding impurities. So for small impurities it's okay, but the next order there's a breakdown. And this has been the focus of a lot of wonder, you know, what's going on here. And we were very puzzled by it. No one's really tried to answer this properly, I think, since 1997. The problem doesn't arise in the Dirac formulation, but what about in the HLR formulation? Well, it turns out that it's just that no one really did the calculation properly. If we do it even working within Hartree-Fock or within a simple RPA theory, so if you want to take into account the effect of impurities, the impurities have an electrostatic potential. The electrostatic potential, of course, is screened largely by the electrons, and that gives a fluctuation in the density of electrons. The fluctuation in the density of electrons gives rise to this fluctuating effective magnetic field, which the composite fermions scatter off. But it doesn't completely screen. There's always some leftover electrostatic potential, and so that breaks the time reversal symmetry effectively, because you can see when there's a positive potential. Okay, there's an increase in the density. There's also an increase in the magnetic field, but then the Fermi wave vector is changed, and vice versa the other way. And it turns out that when you put these both into account, and we've just done a calculation to whoops, what happened here? Somehow the bottom is you just calculate this, and we've done this calculation now to lowest order. Just the lowest order for weak magnetic field, weak impurities at long wavelengths and small densities of impurities, we find out that what happens is that the combination of these two things doesn't give you any skew. The net skew scattering is 0, but there's something called a side jump contribution, which has been known from work in anomalous Hall effect. Every time an impurity is an electron scatters over an impurity, it may be scattered to the left or the right, but in either case, it gets a little bit of a kick, and in the center of the wave packet moves over a little bit of the order of a Fermi wavelength, actually, to the left, each time it scatters through 180 degrees. And this net buildup of constant scattering to the left rather than the right breaks the symmetry between sigma xy and sigma yx. Okay, let's see. So this is called the side jump contribution. I should say that this work is somewhat preliminary. We have to check that all the factors that of 2 pi are right and the signs are right. But at least in terms of parameters, it's exactly what you need to restore this particle-Hole symmetry. And it's based on calculations that Noziere and Levina did for the side jump contribution for the anomalous Hall effect. Okay, I should say that it doesn't seem to be actually necessary to take the limit of m going to 0. This seems to be an emergent particle-Hole symmetry, at least to the second order, just at the half-filled Landau level, even within HLR. Okay, the other important thing are commensurability oscillations. So if you look at nu not equal to a half and look at this finite wave vector conductivity, you get a series of sharp maxima, as I started, oscillations in this in sigma xx of q, which we pointed out, HLR. Related to that, and maybe simpler to talk about, are if you look at the magnetoroton energy spectrum, this is basically the energy spectrum of a bound state of an exciton formed of of a quasi-particle and a quasi-hole, let's say in a nu equals 10^21 quantum state. So we have two 1/21 and minus 1/21. We form a bound state. You get a Rotan spectrum, which naively would just have an energy which is just the energy gap of the nu equals 10^21 state. But because of the interactions, the spectrum oscillates with Q, and as you get closer and closer to nu equals half, these oscillations become larger and larger, and you find that there are a series of very sharp minima in the spectrum at values of Q, which are just the places where the maxima in the conductivity occur. And this also shows up in the behavior of the resistance in the presence of an external potential at wave vector Q. And the predictions of HLR was that these features should occur, the commensurability oscillations that should occur when at the nth value of Q where it occurs is given by Zn over Rc star, where Zn is the position of the nth zero of the first Bessel function. It's roughly 4 times pi. And Rc star is it would be the cyclotron radius in the effective magnetic field delta B, which is given by Kf over the absolute value of delta B. And delta B is the distance from B equals a half. And similar things come out of the Dirac theory, but at the lowest order, they're exactly the same, but there's a slight difference. Because here, if you took this literally, you would say, okay, so Kf, in Dirac theory, Kf is just 1 over the square root of the magnetic field, so this is symmetric in delta B. We're varying delta B by keeping B fixed and varying the electron density, so we get Rc star is the same for delta B and minus delta B. But in the HLR theory, at least naively, you're going to put Kf in is equal to the square root of 4 pi times the density. It's determined by the density of electrons, which is slightly different if you go away from nu equals a half, and that gives you a correction of order 1 plus delta B over B to the 1/2. And this correction is not symmetric because it depends on delta B. It's different if delta B is positive or negative. So it looks like this violates electron-hole symmetry to lowest order. However, it turns out that this is not right, because this naive theory is not really a proper evaluation of the formulas. Even in this paper by Steve Simon, he has formulated in terms of Bessel functions. And if you carry out the Bessel functions, if you put in the formulation not to lowest order, but correct to order 1 over delta B, lo and behold, it turns out that there's a shift. The energy minimum of the magnetoroton is not precisely what you get from this crude argument, but there's a shift, and the shift brings it into precise agreement with what you would expect from particle-hole symmetry, at least to next order in delta B, precise agreement. So it looks like the two theories are in fact the same, and again, it doesn't look like you need to take the limit of m going to 0, or that needs to be checked.
But the result is different from Dirac.
No, the Dirac theory is the same. The Dirac theory, so this shifts, it shifts things in such a way that they move to the Dirac theory, which is halfway. The Dirac theory would give you a result which is halfway in between, say, delta B equals 1/11 and delta B equals minus 1. It would make them equal, whereas here we started out with something which was slightly different, but the shifts bring them back to be the same, at least to the order that we've calculated. And again, we've only really checked it for the Z1 minimum, but I'm pretty sure it's going to work for all of them. So this is still work in progress, but it looks pretty clear that at least at this level, this works. There have been experiments to try to look at this that found some deviations between the pH symmetric Dirac theory and the naive HLR, but since we believe that the correct HLR is the same as Dirac theory, experiments cannot distinguish between them. Only theory can distinguish between them. But the actual minima are slightly, they're not exactly given by either of the theories, so there are additional corrections that need to be understood. And let me just, my time is up, let me just leave these conclusions up there for you to look at. Thank you.
question. So I understand correctly that the two theories are the same in the limit when m goes to 0, or are you making the point that if m not equal to 0, they are still equivalent?
So my claim is that they're the same when m goes to 0, and that the Dirac theory also, you can put a mass in that's not equal to 0, and then you can ask what that says. But if you take the Dirac theory with the Dirac mass equal to 0, that has an exact particle hole symmetry in it. An exact particle hole symmetry we would not expect to get out of our theory for m not equal to 0. However, so far we've actually found that it's more symmetric. We're not claiming that it is, but it looks like it's more symmetric than you would more particle hole symmetric than you might naively expect. So somehow the fixed point, somehow there's some emergent particle hole symmetry in the limit of going to half filling. It's certainly, we don't expect it to be particle hole symmetric at between nu equals a half and nu equals a third and nu equals 2/3, say, in the HLR theory. That I wouldn't expect.
Experiment, I do have to go away from m goes 0.
Right. So I'm saying the lowest. So you can look for what happens. You can try to say what's the difference between nu equals, again, keeping the magnetic field fixed. You can try to say what's the difference between nu plus epsilon, 1/2 plus epsilon and 1/2 minus epsilon, and naively you would predict that there would be deviations to order epsilon, depending on what you're looking at. If it's a quantity that's order unity on the two sides, there would be, you might expect there to be deviations to order epsilon, and we find that's not correct. They're the same up to order epsilon squared. They're the same. They might not be the same to order epsilon cubed or epsilon fourth. So, but at least extrapolating in, there's no, the lowest order. It should be correct. You either have to go away from nu equals a half, or put in impurity. You could sit at nu equals a half on average and put impurities in, which will take you away from nu equals a half on both sides. And again, the lowest order at least, we would expect that you get particle hole symmetry.
So one of the crucial aspects of the Dirac theory is this pi Berry phase for a closed loop around the Fermi.
Yeah. Okay, so actually it doesn't matter. So there are two. You can say there's a Berry phase, and you could ask about Berry curvature. So Berry curvature. So the Dirac theory, the Berry curvature at this Fermi surface is actually 0. There's a Berry phase, but it's entirely down at the bottom of all the Berry phases concentrated far from the Fermi surface. So when you integrate it out, it gives you a contribution, a 1/4 pi contribution to the all it does is give you a 1/4 pi contribution to the 1/2 to the sigma xy, and that's taken into account in other ways for us. But there's no, but we would worry about if there was a Berry curvature, that could affect things like this. Certainly in Nogier-Leviner calculation of the skew scattering of the side jump, that depended on spin-orbit coupling in their case, which did depend on the Berry curvature, not on the Berry phase. So I think if there were differences in the Berry curvature, we might have to look more carefully.
So what are the consequences? And one of the things that this Dirac picture helps you understand simply, and which is related to this Berry phase, is the suppression of 2kF correlators of particle hole symmetry.
Okay, yeah. So we wouldn't. So yes, I agree that that's an. So if you're looking at what happens at 2kF, now you're looking at very short wavelengths. So there are an infinite number of parameters to describe what happens at short wavelengths. You have vertex corrections. You could not. You can, because you have particle hole symmetry, you can understand that certain ones are 0. So things that are 0 by particle hole symmetry you get without doing any calculation. Things that are 0 by particle hole symmetry we would have to do by going a really hard calculation. We'd have to really calculate these these vertex corrections, and the statement is particle hole symmetry tells you that the vertex is 0 for certain things. And of course, you can get it without any work because you've put particle hole symmetry. If you put particle hole symmetry in to begin with, you get particle hole symmetry out without any work. We, as you've seen, in order to get particle hole symmetry, we had to do real calculations that were non-trivial. Okay, so the Dirac theory is better for these kind of things because you can do things without any work. That
But it still requires work because there's despite very phase is what guarantees that at k and minus k the wave function is orthogonal.
Yeah, but I think if I put in particle hole symmetry, what you're calculating are certain response functions vanish, or certain correlation functions vanish. And I say if I put in particle hole symmetry, I get the same. All I have to do is put in, as far as I understand it, all the predictions that you're making of things that vanish are things that I know vanish from particle hole symmetry. Is that not right?
Useful is 2kf suppression. I think it's a bit more delicate because it's so trivial that it vanishes just because of particle hole symmetry.
Yeah.
It clearly has to do with this Dirac structure.
Okay, well then there may well be. You may be right, and maybe there's stuff that we should talk about it that I should understand. If it's not just something that you say is vanishing by particle hole symmetry.
Last question. In the experiments by Shayegan, there was some claim that the low part of the oscillations you needed to understand in terms of majority carriers and minority carriers.
Yeah. So okay. So let me just get. Yeah. So let me just get this back up here. Whoops. That's this experiment that you're talking about by Kamburov, and so that's in Shayegan's group. So yeah, they find the minima, they find a particle hole symmetric minimum, but there is, but it doesn't agree with what you naively predict by either their theory or our theory, which is that you would predict that it's smooth. They're finding corrections which are of order delta b. It's of order delta b squared, which are symmetric on the two sides. And we're saying that the corrections, the anti-symmetric corrections, are absent, but there's still further corrections. So they're saying that they don't get perfect agreement between experiment and theory. Whether they're comparing, that's the same. Whether they're comparing with as far as I can see, it's the same problem. Whether they compare with Dirac theory or with our theory, that there is still some leftover discrepancy. But whether that discrepancy is significant or not is not clear because they have a finite density of impurities. They're trying to measure things that are just at the bare, the experimental uncertainties are pretty big, and nobody has been able. We certainly haven't done a calculation specifically for their problem, which requires impurities taken into account to second order, and it's a very complicated problem. We only really did a simpler problem, which is this the magneto-roton minima thing. But assuming that it all goes through, I think the discrepancy, the remaining discrepancy that they find is one that we don't. No, there is still a remaining discrepancy, but it's hard to say how significant it is. But they do find particle hole symmetry, and we have no problem with particle hole symmetry.